KGBI, a radio station in Nebraska, experienced frequent lightning strikes that damaged equipment and disrupted broadcasts. The station implemented comprehensive lightning protection measures. These measures included a network of lightning rods, conductors, and grounding electrodes designed to safely redirect lightning energy into the ground. A radio frequency shield, a conductive mesh, was installed over the antenna tower to provide additional protection from electromagnetic fields. Multiple deep-buried ground rods were used to enhance electrical conductivity and dissipate lightning currents into the earth. All electrical wiring was properly insulated and grounded to minimize potential lightning damage. After implementing these measures, KGBI experienced a significant reduction in lightning strikes. The new lightning protection system effectively redirected lightning energy away from the antenna tower and other vulnerable areas. The lightning protection measures prevented damage to broadcasting equipment and ensured uninterrupted broadcasts. The radio frequency shield allowed for improved broadcasting efficiency by reducing interference from electromagnetic fields. The lightning protection upgrades provided KGBI with enhanced safety for staff and equipment, uninterrupted broadcasting services, improved antenna performance, and peace of mind knowing that the station was protected from lightning strikes. By implementing comprehensive lightning protection measures, KGBI radio station significantly mitigated the risk of lightning strikes, ensuring the safety of its equipment and the continuity of its broadcasts. The case study highlights the importance of proactive lightning protection for radio stations and other facilities vulnerable to lightning damage. Lightning protection systems are designed to minimize the impact of lightning strikes on structures and equipment. These systems typically consist of several key components. Firstly, air terminals, also known as lightning rods, which are installed on the highest points of a structure to intercept lightning strikes. Secondly, down conductors, which are heavy gauge wires that provide a low resistance path for the lightning current to flow from the air terminals to the grounding system. Thirdly, grounding electrodes, which are buried in the earth and provide a point of discharge for the lightning current, dissipating it safely into the ground. The effectiveness of a lightning protection system depends on several factors, including the design and installation of the system, the soil conductivity, and the frequency and intensity of lightning strikes in the area. Regular inspection and maintenance are essential to ensure that the system remains in good working order. Grounding is a critical aspect of electrical safety, and it plays a vital role in protecting people and equipment from electrical shock and damage. A grounding system provides a low resistance path for fault currents to flow back to the source, allowing overcurrent protection devices such as circuit breakers or fuses to quickly trip and energize the circuit. There are several types of grounding systems, including equipment grounding, which connects non-current carrying metal parts of electrical equipment to ground, and system grounding, which connects the neutral point of a power system to ground. Proper grounding is essential for minimizing the risk of electrical shock, preventing equipment damage, and ensuring the safe and reliable operation of electrical systems. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. Bonding refers to the practice of connecting together all metal parts of an electrical system to create a low impedance path for fault currents. Bonding helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electrical shock. The NEC specifies the types of conductors that can be used for grounding and bonding, as well as the methods for connecting them. It also includes requirements for grounding electrodes such as ground rods, ground plates, and underground metallic water pipes. Compliance with the NEC grounding and bonding requirements is essential for ensuring the safety and reliability of electrical systems. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, also known as transient overvoltages. Voltage surges can be caused by lightning strikes, switching of electrical loads, or other disturbances on the power system. SPD work by diverting the surge current to ground, preventing it from reaching sensitive equipment. There are several types of SPD, including surge arresters, which are typically used for high voltage applications, and transient voltage surge suppressors, or TVSSs, which are used for low voltage applications. SPD are typically installed at the service entrance of a building or at individual equipment locations. The selection of an SPD depends on several factors, including the voltage rating of the equipment being protected, the expected surge current, and the application. Proper installation and maintenance are essential to ensure that SPD function correctly. Electrical safety is a critical concern in all types of facilities, including radio stations. Electrical hazards can cause serious injuries or even death. To minimize the risk of electrical accidents, it is essential to follow safe work practices and use appropriate personal protective equipment, or PPE. Some common electrical safety practices include de-energizing circuits before working on them, using lockout-tagout procedures to prevent accidental re-energization, and wearing insulated gloves and eye protection. It is also important to regularly inspect electrical equipment for damage and to repair or replace any defective equipment. Training is essential for all personnel who work with or around electrical equipment. The National Fire Protection Association, or NFPA, develops standards for electrical safety, including NFPA 70E, Standard for Electrical Safety in the Workplace. This standard provides guidance on how to protect workers from electrical hazards. The Occupational Safety and Health Administration, or OSHA, also has regulations for electrical safety. These regulations require employers to provide a safe workplace and to train employees on electrical safety procedures. The selection of appropriate wiring methods is essential for ensuring the safe and reliable operation of electrical systems. There are several types of wiring methods, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic conduit. The choice of wiring method depends on several factors, including the environment, the voltage, and the type of occupancy. The NEC specifies the types of wiring methods that can be used in different applications. It also includes requirements for the installation of wiring, such as the spacing between supports, the bending radius of conduits, and the protection of wiring from physical damage. Proper wiring practices are essential for preventing electrical fires and ensuring the safety of electrical systems. Power quality refers to the characteristics of the electrical power supply, including voltage, frequency, and waveform. Poor power quality can cause equipment malfunction, damage, and downtime. Some common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are short-term decreases in voltage, while voltage swells are short-term increases in voltage. Harmonics are distortions of the voltage or current waveform. Transients are short-duration, high-amplitude voltage spikes. There are several ways to improve power quality, including using surge suppressors, installing harmonic filters, and using uninterruptible power supplies. Power quality monitoring equipment can be used to identify and diagnose power quality problems. Electromagnetic interference, or EMI, is a disturbance that affects electrical circuits due to electromagnetic radiation emitted from an external source. EMI can cause equipment malfunction, data loss, and communication problems. There are several sources of EMI, including radio transmitters, microwave ovens, and industrial equipment. There are several ways to reduce EMI, including shielding, filtering, and grounding. Shielding involves enclosing electrical equipment in a conductive enclosure to block electromagnetic radiation. Filtering involves using filters to remove unwanted frequencies from the electrical signal. Grounding involves providing a low impedance path for electromagnetic radiation to ground. Copper is an excellent conductor of electricity and is widely used in electrical wiring and grounding systems. Copper has several advantages over other conductors, including its high conductivity, corrosion resistance, and ductility. Copper is also relatively easy to solder and connect. The Copper Development Association provides information and resources on the use of copper in electrical applications. The NEC specifies the allowable ampacities of copper conductors. Ampacity is the maximum current that a conductor can carry without exceeding its temperature rating. The ampacity of a conductor depends on several factors, including the size of the conductor, the insulation type, and the ambient temperature. Regular maintenance is essential for ensuring the safe and reliable operation of electrical systems. Maintenance activities can include inspecting equipment for damage, cleaning equipment, tightening connections, and testing equipment. A preventive maintenance program can help to identify and correct potential problems before they lead to equipment failure or safety hazards. Electrical testing equipment is used to measure electrical parameters such as voltage, current, resistance, and impedance. Common electrical testing equipment includes multimeters, clamp-on ammeters, insulation resistance testers, and ground resistance testers. It is important to use the correct testing equipment for the application and to follow safe testing procedures. Arc flash is a dangerous electrical hazard that can occur when a high voltage arc is formed between two conductors. Arc flash can cause severe burns, blindness, and even death. Arc flash hazards can be reduced by following safe work practices, such as de-energizing circuits before working on them, using arc-rated personal protective equipment, and maintaining safe working distances. An arc flash hazard analysis can be used to determine the potential arc flash hazard levels and to select appropriate personal protective equipment. The 2017 NEC provides requirements for arc flash hazard assessment and mitigation. The station implemented a comprehensive lightning protection system, a network of lightning rods, conductors, and grounding electrodes designed to safely redirect lightning energy into the ground. The radio frequency shield is a conductive mesh installed over the antenna tower to provide additional protection from electromagnetic fields. Multiple deep-buried ground rods enhance electrical conductivity and dissipate lightning currents into the earth. Proper wiring means all electrical wiring was properly insulated and grounded to minimize potential lightning damage. A significant reduction in lightning strikes, by 95%, was achieved by redirecting lightning energy away from the antenna tower and other vulnerable areas. The lightning protection measures prevented damage to broadcasting equipment and ensured uninterrupted broadcasts. The radio frequency shield allowed for improved broadcasting efficiency by reducing interference from electromagnetic fields. Lightning protection upgrades provided enhanced safety for staff and equipment. They also gave uninterrupted broadcasting services. There was also improved antenna performance and peace of mind knowing that the station was protected from lightning strikes. It ensured the safety of its equipment and the continuity of its broadcasts. The case study highlights the importance of proactive lightning protection for radio stations and other facilities vulnerable to lightning damage. The 2017 NEC Article 250 provides comprehensive requirements for grounding and bonding electrical systems, ensuring safety and minimizing electrical shock hazards. Section 250.4 addresses general requirements for grounding, outlining the need for effective ground fault current paths and minimizing voltage to ground. Grounding electrode systems, as detailed in Section 250.50, must be interconnected to create a robust, low-impedance path to Earth. Acceptable grounding electrodes, covered in Section 250.52, include metal underground water pipes, ground rings, and rod and pipe electrodes, each with specific installation requirements. Grounding conductors, addressed in Section 250.62, must be properly sized and identified with specific rules for different types of systems and equipment. Equipment grounding conductors, as outlined in Section 250.118, provide a path for fault current from equipment back to the source, ensuring proper operation of overcurrent protection devices. Bonding, covered in Section 250.92, ensures electrical continuity and the capacity to safely conduct fault current. Surge protection devices, addressed in Article 280 of the 2017 NEC, protect electrical systems from transient overvoltages. Section 280.4 requires surge protection devices to be listed and labeled for their intended use. Installation requirements, as detailed in Section 280.21, specify proper wiring and connection methods. The location of surge protection devices, covered in Section 280.22, should be at the service entrance or on specific equipment to minimize voltage surges. The proper selection of surge protection devices, addressed in Section 280.6, depends on the voltage and current requirements of the protected equipment. Regular inspection and maintenance, as outlined in Section 280.5, ensure continued protection. The copper ore case study exemplifies the importance of comprehensive lightning protection, grounding, and surge protection measures in critical facilities like radio stations.